Close your eyes and imagine the boundless expanse of space stretching out before you, a vast canvas of darkness and light. Stars twinkle in the distance like tiny beacons in the night, while planets spin slowly in their eternal dance. The silence here is so profound that you can hear your own breath slowing with each passing moment. Tonight, we'll embark on a journey through the depths of the universe, where there's no room for hustle or worry, just the gentle glow of distant galaxies and a peace that wraps around you like a warm blanket, carrying you into a world of sweet dreams. In 2003, astronomers discovered a dwarf planet in the Kuiper Belt, which they named Sedna. At that time, it was the most distant object known in the solar system. The discovery of Sedna was revolutionary. Among other things, it played a role in Pluto losing its status as the ninth planet. Sedna provided the final confirmation to scientists that the Kuiper Belt is a veritable treasure chest for astronomers. Most importantly, its discovery reignited discussions about the existence of a ninth planet, a search that had been ongoing unsuccessfully since the 19th century. There were solid reasons for such discussions. On the outskirts of the solar system, there exists a massive object that alters the trajectories of smaller celestial bodies. Their orbits deviate from their original paths, clearly influenced by some gravitational source. These elliptical orbits consistently point in the same direction and deviate by the same degree. Today, scientists Michael Brown and Konstantin Batygin are nearly certain that this is indeed the ninth planet, and they seem prepared to dedicate their entire careers to this discovery. However, not everyone agrees that it is a planet. Some scientists suggest that these gravitational distortions might actually be caused by a black hole. This isn't the kind of massive black hole formed by the gravitational collapse of a star, but rather a very small, compact one, perhaps the size of a bowling ball or even a tennis ball. Such objects, known as primordial black holes, could be scattered throughout the universe in great numbers. The existence of primordial black holes was first proposed by Soviet scientists Yakov Zeldovich and Igor Novikov in the late 1960s. Their idea was based on the Big Bang model. Let's travel back 13.7 billion years. Imagine the Big Bang has just occurred, and our universe, still minuscule, was an incredibly hot and dense point. Due to the extreme temperatures, its state was unstable, and as it evolved, a crucial event took place. Gravity separated from the other three fundamental forces: electromagnetic, weak nuclear, and strong nuclear forces. This period in the universe's life lasted just 1/6 of a second, and is known as the Planck epoch. By the end of this period, the universe was still microscopic, measuring just 1 Planck length across, yet it already contained all the ingredients necessary to form the universe as we know it today. After the Planck epoch, pressure and temperature remained extraordinarily high. Density fluctuations and uneven conditions could have triggered gravitational collapse in the densest regions, forming primordial black holes. Zeldovich and Novikov's hypothesis was first taken up and thoroughly explored by Stephen Hawking in 1971. He calculated that such black holes might have the mass of an average-sized asteroid. Today, scientists identify 3 mass ranges in which primordial black holes might exist. One roughly equivalent to small asteroids, another to planetoids, and a third to masses of a few suns. However, since primordial black holes didn't form from stellar collapse, they could theoretically be of any size. The smallest class has likely vanished by now, as the lower the mass, the stronger their radiation and the faster they lose mass. This process, known as Hawking radiation, accelerates and ends in a burst. yet no such bursts have been observed. Moreover, these objects lack sufficient mass to actively accrete material and form a bright accretion disk, making them even harder to detect. Primordial black holes in the second and third mass ranges differ from stellar collapse black holes only in that they don't initially rotate, so they might be detected through phenomena like gravitational lensing, the bending of light rays in the gravitational field of massive objects. Stephen Hawking suggested that primordial black holes should be relatively abundant near our Milky Way. If so, given that many formed in the early stages of the Big Bang, they should still exist today, and we ought to observe them. However, no one has yet managed to do so, leaving primordial black holes in the realm of hypothesis. If they do exist, though, they could help solve major cosmological mysteries, particularly the problem of dark matter. In 1994, three Russian astrophysicists, Pavel Ivanov, Pavel Naselsky, and Igor Novikov, published a paper estimating the number of primordial black holes with masses around 1/10 that of the Sun. They suggested that under certain conditions, enough of these objects could have formed to account for effects typically attributed to dark matter. At the very least, primordial black holes could contribute significantly to the universe's unseen mass. Current estimates suggest dark matter accounts for about 25% of the universe's unaccounted mass. An invisible yet massive primordial black hole makes an excellent candidate for dark matter. Primordial black holes have also been linked to the merging of black hole pairs. It's not easy to imagine how such pairs could form. If they originated from massive stars, all models of massive binary star evolution suggest that one star would become a black hole before the other, siphoning material from its companion's outer layers. This would, in theory, prevent the second star from becoming a black hole as well. It is assumed that these are simply primordial black holes of moderate mass. They were never stars. Alternatively, another hypothesis links primordial black holes to supermassive black holes at the cores of galaxies. In other words, it wasn't galaxies that formed black holes, but black holes that enabled galaxies to form. Today, we already know of quasars, objects with supermassive black holes at their centers, observed at redshifts corresponding to events as old as 12.9 billion years or less. What's particularly striking is that the mass of black holes at the centers of such quasars is hundreds of times greater than that of Sagittarius A, the supermassive black hole at the center of our Milky Way. Yet our galaxy is quite old, and 12.9 billion years ago, the universe itself wasn't even a billion years old. So when did these dozens of black holes manage to accumulate such enormous mass? An accretion disk, through which a black hole captures matter, allows it to grow at a rate no faster than millions of solar masses per billion years. Similar problems arise with galaxies. The youngest of them formed just 400 million years after the Big Bang, though theoretically, there wasn't enough time for a sufficient number of stars to form. This leads to the idea that primordial black holes acted like seeds of the Big Bang, dramatically accelerating galaxy evolution by gathering matter from their surroundings through gravitational pull. This all sounds promising, but how do we detect primordial black holes and resolve all doubts about their existence? Surprisingly, there are many options, though only a few can be practically applied today. The rest are theoretical and will require extensive research and a lot of time to test. For instance, such compact objects could cause changes in the brightness of gamma-ray bursts, when passing near their line of sight due to gravitational lensing. Another method of detecting primordial black holes might involve observing ripples on the surface of stars. If a black hole passed through a star, its density would cause observable oscillations. In the near future, scientists will actively test yet another theory. Suppose tiny primordial black holes evaporated long ago. However, if a fourth spatial dimension existed, as predicted by string theory, it would affect how gravity operates on small scales, significantly slowing evaporation. In that case, a few thousand black holes might still remain in our galaxy. To test this theory, scientists will use the Fermi Gamma Ray Space Telescope. They might kill two birds with one stone, detecting both primordial black holes and making a major step toward proving string theory. Meanwhile, Michael Brown and Konstantin Batygin face a similar situation with the hypothetical ninth planet of our solar system. So far, they have only mathematical calculations based on studying the peculiarities of Sedna's motion. Later, Brown and Batygin analyzed the motion of 6 randomly selected, highly distant Kuiper belt objects. Based on the alignment of their parameters, they demonstrated the presence of a cosmic body with a mass greater than Neptune's and a diameter 2 to 4 times that of Earth, influencing these objects. The probability of this alignment is so high that scientists don't seriously consider it a random coincidence. These 6 objects have highly elongated orbits that twist in a way that makes them nearly perpendicular to the solar system's disk. In favor of the idea that this isn't a planet, but a primordial black hole, are the peculiarities of light distortion passing through its presumed location. It could be the size of a soccer ball while having a mass 10 times that of Earth. Regardless, both theories, however coherent, remain on paper for now. What would be the most irrefutable proof of a primordial black hole or Planet 9? Exactly, a photograph from a telescope. The near future will reveal what lies in the Kuiper belt. Optimism comes from the fact that Neptune's existence was once just a mathematical prediction too. Everything that collides with it, crosses its path, or even brushes against it inevitably falls inward. Then, due to the conservation of energy, the mass of the black hole increases. This process happens with every black hole we know of. Material from other stars, cosmic dust, interstellar matter, gas clouds, even radiation and neutrinos left over from the Big Bang, all of it gets pulled in. Any matter that encounters a black hole adds to its mass. The growth of black holes depends on the density of the matter and energy surrounding them. The monster at the center of our Milky Way grows at a rate of 1 solar mass every 3,000 years. By contrast, the black hole at the center of the Sombrero Galaxy grows even faster, 1 solar mass every 20 years. The larger and heavier a black hole is, on average, faster it grows depending on the material it encounters. Over time, its growth rate slows, but since the universe is only about 13.8 billion years old, black holes are still thriving. On the other hand, black holes don't just grow over time. There's also a process of evaporation, Hawking radiation. This is tied to the fact that space is heavily curved near the event horizon, but flattens out farther away. From a great distance, you can observe faint radiation emitted from the curved region near the event horizon. Linked to the quantum vacuum having different properties in different curved regions of space. The end result is that black holes emit black body thermal radiation, mostly in the form of photons, in all directions around them. within a volume of space roughly encompassing about 10 Schwarzschild radii from the black hole's location. It might seem strange, but the smaller the black hole, the faster it evaporates. Hawking radiation is an incredibly slow process. A black hole with the mass of our Sun would evaporate in 10 to 64 years. The one at the center of our Milky Way would take 10 to 87 years, and the most massive ones in the universe, 10 to 100 years. A black hole with the mass of Earth would last 1047 years. One with the mass of the Great Pyramid of Giza, 6 million tons, would take about 1,000 years. With the mass of the Empire State Building, about a month. And with the mass of an average human, a picosecond. The smaller the mass, the faster the black hole evaporates. As far as we know, the universe could contain black holes of unimaginably diverse sizes. If it were filled with lightweight black holes, up to 1 billion tons, they would all have evaporated by now. There's no evidence of black holes existing with masses between these lightweight ones and those born from neutron star mergers, which theoretically have about 2.5 solar masses. Above these limits, X-ray studies suggest the existence of black holes in the 1020 solar mass range. The LIGO Observatory has detected black holes from 8 to 62 solar masses. And of course, supermassive black holes are found throughout the universe. Today, all existing black holes are gaining matter faster than they lose it through Hawking radiation. A solar mass black hole loses about 10 to 28 joules of energy per second. But considering that even a single photon of cosmic background radiation has 1 million times more energy, with 411 such photons per cubic centimeter left from the Big Bang, moving at the speed of light and colliding 10 trillion times per second in every cubic centimeter. Even an isolated black hole in the depths of intergalactic space would have to wait until the universe matures to 10 to 20 years. That's 1 billion times its current age before its growth rate drops below the rate of Hawking radiation. Suppose you're in intergalactic space, far from ordinary matter, dark matter, cosmic rays, stellar radiation, and neutrinos, with only the photons left from the Big Bang. How massive would your black hole need to be for the rate of evaporation, Hawking radiation, and the absorption of photons growth to balance each other? The answer comes out to around 10 to 23 kilograms, roughly the mass of the planet Mercury. If Mercury were a black hole, it would be 0.5 millimeter in diameter and radiate about 100 trillion times faster than a solar mass black hole. At that mass in our universe, a black hole would absorb as much microwave background radiation as it loses through Hawking radiation. The chain of thermonuclear fusion culminates with iron. When iron nuclei fuse with others, energy is no longer released. Instead, it is consumed. At this point, the star's evolution halts. By then, it has become a layered structure, like an onion, with each layer corresponding to a specific stage of its development. On the outside lies a hydrogen shell, beneath which are layers of helium, carbon, oxygen, silicon, and at the core, a nucleus of compressed gaseous iron heated to several billion degrees. This core is so densely packed that a gaming die made of this material would weigh 10,000 tons. Eventually, the pressure in the growing iron core can no longer withstand the force of its own gravity, and it collapses in a fraction of a second. Matter exceeding the mass of the Sun compresses into a sphere just 20 kilometers in diameter. Under gravity's influence, negatively charged electrons in the core are forced into positively charged protons, forming neutrons. From this core emerges a neutron star, a dense clump of so-called exotic matter. The neutron star can no longer compress further. Its surface becomes an impenetrable barrier, rebounding the material from the upper layers that gravity pulls inward. An internal explosion triggers a reverse shockwave that surges outward through all the layers. In the process, the matter becomes extraordinarily hot. Near the core, temperatures reach 50 billion degrees Kelvin. As the shockwave reaches the star's outer shell, a fountain of superheated gas erupts into space at speeds exceeding 40,000 kilometers per second, emitting light in the process. The star flares brightly. This flare is what astronomers observe through telescopes thousands or even millions of years later, when the light reaches Earth. Computer models programmed with the laws of physics reveal that complex thermonuclear reactions occur in the infernal blaze around the neutron star. Lightweight elements like oxygen and silicon burn into heavier ones: iron, nickel, titanium, and calcium. For a long time, it was believed that the heaviest chemical elements, gold, lead, and uranium, were born in this cataclysm. However, recent calculations and simulations suggest that the power of the particle winds from a supernova is insufficient to force free neutrons into the scattering atomic nuclei to form increasingly heavy aggregates. So where do these heavy elements come from? They are born from the collision of neutron stars left behind after supernova explosions. Such collisions result in a colossal ejection of incandescent matter into space. Moreover, the frequency distribution of heavy elements in this material, as derived from simulations, matches the actual parameters of our solar system. Thus, supernovae have lost their monopoly on creating cosmic matter, but it all begins with them. Supernovae vibrate like giant speakers, emitting an audible hum before their explosion. Then, at the moment of detonation and during their transformation into an expanding nebula, they become a mesmerizing spectacle. Yet, paradoxically, in physical terms, this grand cosmic fireworks display, though dramatic, is merely a byproduct. During a star's gravitational collapse, more energy is released in a single second than all the stars in the universe emit in their normal state combined. 99% of this energy is released not through the visible flare, but in the form of invisible neutrino particles. In about 10 seconds, an immense number of these ultralight particles form in the star's iron core. Detecting traces of these particles is extremely difficult because they barely interact with matter. Yet without these elusive neutrinos, the cosmic fireworks could not ignite. To uncover the mechanism behind the supernova's secondary detonation, scientists have conducted numerous computer simulations over the years. After extensive research, the process has been explained as follows. In the star's hot layers, funnels and bubbles form, resembling the surface of simmering porridge. Additionally, the churning matter oscillates between the shell and the core, prolonging its exposure to high-energy neutrinos streaming from the star's depths. These neutrinos impart the momentum needed for the explosion. Ironically, these neutral particles, which typically pass through matter without a trace, serve as the detonator for the supernova. Supernova explosions play a leading role in the universe's evolution, ejecting vast amounts of dust far into interstellar space. After the explosion of a star, initially 10 times the mass of the Sun, what remains is a neutron star weighing just 1.5 solar masses. Most of the material scatters into space. This powerful wave of matter and energy triggers the formation of new stars. Sometimes supernova explosions are so forceful that they expel gas from the star's shell beyond its parent galaxy, dispersing it into intergalactic space. Astrophysical computer models suggest this effect is even more critical for cosmic evolution. If the gas remained within galaxies, far more new stars would form. The abundance of stardust and heavy element particles in the universe indicates how frequently supernovae occur. Every second, between 5 and 10 stars explode somewhere in the cosmos. Astronomers eagerly await supernovae in our own galaxy. Observing a star's explosion up close surpasses even the most advanced computer models. According to their predictions, 2 aging stars in our vicinity should detonate within the next century. The most likely candidate is the red supergiant Betelgeuse, located in the upper left corner of Orion, the most beautiful constellation visible in the night sky. If this star were at the center of our solar system, it would extend far beyond the orbits of Earth and even Mars. Over millions of years, Betelgeuse has exhausted most of its nuclear fuel and could explode at any moment. Before its demise, this giant will flare thousands of times brighter than it shone in life. Betelgeuse will blaze in the sky like a crescent, or even a full moon, say astronomers. If we're lucky, its glow might even be visible during the day. But that's just an example. For a realistic black hole, you can't isolate it from the rest of the universe's matter. Even black holes ejected from galaxies still pass through the intergalactic medium, encountering cosmic rays, starlight, neutrinos, dark matter, and all sorts of massive and massless particles. You can't escape the cosmic microwave background no matter where you go. Black holes constantly absorb matter and energy, growing in mass and size. Yes, they also emit energy, but for all the black holes in our universe to start losing mass faster than they gain it, about 100 quintillion years would need to pass, and complete evaporation would take even longer. Well, it seems black holes might outlast everything and everyone. What do you think? Let me know in the comments. Also, check if you've hit the bell icon so you don't miss the next video. It'll be even more exciting. And of course, don't forget to give this video a thumbs up. Until next time, see you in more fascinating adventures. The Giant Crab Nebula in the constellation Taurus. It formed from a supernova explosion, one of the most spectacular events in the universe. The resulting nebula is a glowing gas cloud, shining in both optical and infrared ranges, expanding at 1,500 kilometers per second. At its center lies a neutron star, the compressed core of the original star. Supernova explosions accelerate the cosmic cycle of matter's birth and decay. Shock waves from these explosions ripple through space like waves on water. Compressing interstellar gas into giant filaments, they trigger the formation of new planets and stars. They even influence our lives here on Earth. Nearly all the elements that make up us and our world originated from supernova explosions. The calcium in our bones, the iron in our blood, the silver in our jewelry, all of it was born in the crucible of cosmic blasts. In the stellar furnace, atoms of these elements fuse together before being hurled into interstellar space by a mighty blast. Both humanity and everything around us are nothing less than stardust. But how do these cosmic nuclear furnaces work? Which stars end their lives in an explosion? And what triggers the detonation? A major boost for modern supernova research came from the astronomical sensation of the century. It happened in 1987. The discovery of a supernova, coded SN 1987A, swept the world and caused a global stir. It was spotted in the nearby Large Magellanic Cloud galaxy, just 160,000 light-years from Earth, a stone's throw by cosmic standards. A striking coincidence, the star's grand demise began 160,000 years ago, when a unique primate species, Homo sapiens, emerged on the savannas of East Africa. By the time its light reached Earth, humans had populated the planet, invented the wheel, developed agriculture and industry, unraveled complex laws of physics, and built powerful telescopes, just in time to capture and analyze the light signal from the Magellanic Cloud. Today, this supernova remains the most studied in astronomical history. Analysis of its radiation led, among other things, to the conclusion that there are two main types of supernovae. Type 1 supernovae draw their explosive energy from rapid thermonuclear fusion in the dense carbon-oxygen core of small stars, about the size of the Moon, and with a mass equal to our Sun. Their flashes are ideal for studying the accelerated expansion of the universe. Type 2 supernovae involve a collapsing core. Here, the explosive energy comes from gravity, which compresses the material of a star at least 8 solar masses, causing it to collapse. These explosions are detected 3 times more often and create the conditions for forming heavy elements like silver and cadmium. SN 1987 belongs to the second type. This is evident from the size of the star responsible for the cosmic upheaval. It was 20 times more massive than the Sun and followed an evolution typical of stars in that weight class. A star begins its life as a cold, diffuse cloud of interstellar gas. Under its own gravity, it compresses and gradually takes the shape of a sphere. Initially, it consists mostly of hydrogen, the first chemical element to emerge shortly after the Big Bang, which marked the start of our universe. At the next stage of a star's life, hydrogen nuclei fuse to form helium. This nuclear fusion releases an enormous amount of energy, which causes the star to shine. From the accumulating helium, increasingly complex elements are synthesized, first carbon, then oxygen. As this process continues, the star's temperature rises and heavier atoms form in its fiery depths.